So on this quiz, we had a sphere, it had a radius a, and it had a non-uniform charge density. And we went through and we used Gauss's law to figure out the electric field, and then we were asked to determine what the voltage at the center was. Now, we actually didn't have to use Gauss's law to figure out the electric field at the center. We could have just claimed, hey, it's the center of a symmetric situation, so E is just equal to 0. We did use Gauss's law so we could integrate the electric field from infinity down to 0 to figure out the voltage at the center, but then somebody asked, well, that seems kind of excessive. Couldn't we just integrate the charge and just use V is equal to the integral of K Q over R? If it's the integral, that'd have to be a dq there. And I said, yeah, that should be right. Let me go home and think about it. I didn't want to do too many gymnastics in front of a class without taking 5 minutes to just think out of a plan of attack. But in theory, it should work. Now, the first thing I would want to do is I'd want to say, hey, we got this far. What would it actually look like if we evaluated these integrals? And you say, okay, well, we could go and look at this, and this would be 3/4 epsilon naught a to the 4th power. Now I'm going to go and I'm going to reverse the limits of integration, get rid of my minus sign there. And this would just be dr divided by r squared. And when we do that, we're basically going to get a 1 over r. So this ends up being 3/4 epsilon naught a to the 4th power. And this is going to be 1 over r from a to infinity. The infinity turns into 0, so this ends up being 3/4 1 over epsilon naught a to the 3rd power. Okay. The second integral here, we're going to do the exact same thing. We're going to flip the limits of integration. And we're going to evaluate the integral. So we'd have a 3/4 epsilon naught r squared dr. I'm going to pull the constants out front because I'm a pull the constants out front kind of guy. And yeah, this is a nice happy polynomial that even Marasco can do, so that is going to be an r cubed divided by 3, so I can get rid of my 3 out front. So this is 1 over 4 epsilon naught r cubed evaluated from 0 to a. And what we get there is going to be, well, 1 over 4 epsilon naught a cubed. Okay, we did a little bit of hand is faster than the eye. When I do this integral, I should get a minus sign. That's why this ends up being positive when I think about these limits. But overall, I should be getting a cubed for epsilon naught, which is a nice clean answer. Okay, so we're going to compare that to what we would get if we had simply integrated over the entire volume of the sphere of k dq over r. Okay. Now in class I was a little worried about this because there are a whole lot of r's floating around. Okay. This is always going to be the r between your point of interest and the little tiny chunk of charge that you're evaluating. But we're in a nice spherically symmetric situation. We're thinking about the voltage at the origin. So that r is basically going to be the same r as just a measurement from the center of the sphere, because we're measuring to the center of the sphere. So this makes life nice and simple. Life is nice and simple. Okay, and that was the main thing I was worrying about in class. I was pretty sure that that's what we were going to run into, but if not, then we would be in trouble. Okay, so it's important that we can actually identify the r in the denominator with just the variable r. It's not going to take on two different meanings. Technically, it is taking on two different meanings, but those meanings are coincident. Okay, the r, which means the distance between the point charge and where I'm evaluating, is always going to equal the distance between the center of the sphere and where I'm at that particular place in my evaluation. Okay, so I picked a very special place, and that allows me to do this. So then we turn around and say, okay, well, K, well, this is the problem. This is not from 0 to A. This is from 0 to Q, however much charge we've got here. We're integrating over Q, and what we really want to do is take that from, well, some place which is physical to some other place which is physical, and integrate over some physical variable. Okay? Because integrating over Q, well, yeah, that's kind of conceptually clear, but computationally not so clear in most times. And usually what we do is we say, well, dq, the amount of q we have, is going to equal to a charge density multiplied by some dv. And the natural dv to take here is just going to be a very thin shell. And you say, why a very thin shell? Because over a thin shell, r is constant. And our rho is a function of r. Okay? So dq is going to equal rho as a function of r, which in this case is 3 times r, multiplied by, well, what is the volume of a very thin shell? I'll go back and I'll say you can either do calculus and evaluate all the d phis and the d thetas and the drs, or you can just take a sort of physical explanation and say, if I want to know the volume of a very thin shell, I would take the surface area of that shell and multiply it by an infinitesimal thickness. In other words, 4 pi r squared, the surface area, dr, and the people who have done a lot of calculus can kind of look at that and say, yeah, that's exactly what it should be. So now we go back and we say we're integrating over r, so we should go from 0 to the edge of the sphere, because once you're outside of the sphere, you run out of charge, so you're not counting up charge anymore. Your dq goes to 0. Of k multiplied by 3r times 4 pi r squared dr, all divided by r. Well, again, I may take the constants out of the integral type of guy, so I'm going to have k times 3 pi times 4 pi r squared, which is 12 pi. I have to leave all of those r's, r squareds, r everything inside, so I'm going to have an r cubed on the top, an r on the bottom, dr. So that's going to get me a k times 12 pi, and that's going to be an r squared, and Marasco can show that he can integrate r squared like that. So now I'm left with k. I can get my 12 and my 3 to go away. 4 pi a cubed. And we're almost there because we can remember that k is equal to 1 over 4 pi epsilon naught. So we have 4 pi divided by 4 pi epsilon naught a cubed, which is going to equal a cubed over epsilon naught, which is going to be the exact same answer. Okay? Well, that's not so bad. You say, why didn't we do it that way to begin with? Well, a couple reasons. First of all, that right there. If you've taken enough math classes, then that's kind of an intuitive, straightforward thing to do. If you haven't had enough math classes, then you just look at that and say, I can kind of believe that argument, but I wouldn't know that I'd come up with it on my own. And Gauss's law, I know Gauss's law, I can always just integrate against the electric field. Secondly, I really do want people to practice Gauss's law. Gauss's law is good for you. And thirdly, this only worked because we were finding the voltage at the center. So you can imagine, I say, instead of finding the voltage at the center, I find the voltage at some distance small d from the center. In that case, you're still going to be able to solve that using Gauss's law, doing the exact same thing we did before. We would just change this guy from 0 to d. On the other hand, when I tried to integrate over all of my parts, it's not integration by parts, it's integrating over a whole bunch of parts here. Now when I did a k dq over r, as I'm integrating over this charge, my r is going to be measured to that point right there. And I'm not just going to be able to say that that is going to be r as in the measure your distance from the center of the sphere r. It's going to be something decently more ugly and complicated, and we would not be able to approach the problem this way. But if you have the symmetry that you had in the original problem, I really like the way of just integrating over the volume of that sphere and getting the voltage at the center.